Now we're going to discover other useful properties of the incircle and the excircles. Suppose first that I have a triangle with an incircle inscribed in it. Then if I call this segment x, then the length of this segment will also be x. Similarly, if this is y, then this is also y, and if this is z, then this is also z. Then the perimeter of the triangle, which is the sum of the sides, would be 2 times x plus 2 times y plus 2 times z. And so the semi-perimeter, which is half of the perimeter, would be just x plus y plus z because the 2's are going to cancel out. We can rewrite this as s minus x minus y equals z. Now let's call this side C, this side A, and this side B. Then z equals s minus c because x plus y equals c, as you can see here. Similarly, from this equation we can get that y equals s minus b and x equals s minus a. And therefore, we can rewrite the labels on this diagram. So this segment equals s minus a, this equals s minus b, and this equals s minus c, where s is the semi-perimeter and a, b, and c are the sides of the triangle. Now let's see what happens when we consider the excircle of the triangle. Let the excircle touch the sides of the triangle at this point, and this point. Now let's denote this segment by m and this segment by n. We know that this equals this, and we know also that m, this segment, equals this one. Now let's remind ourselves that this side here is c, and it equals m plus n. This side here is b, and this side here is a. And so, if we take this segment, it equals this segment here. That's because they're both tangent to this excircle here. But their sum, the sum of this segment and this segment, would be b plus a plus m plus n. But m plus n is also this thing, which is c. So it would be b plus a plus c. And then because this equals this, then one of them is the sum divided by 2, which is a plus b plus c divided by 2, which is the semi-perimeter. And so this distance here from the vertex to the point where the excircle is tangent to this side is the semi-perimeter. And now, since this here is the semi-perimeter and this here is b, then this length is semi-perimeter minus b, so s minus b. And similarly, this here is the semi-perimeter and this here is a, so this here, this segment, is s minus a. But we know that this length equals this length and this length equals this length. And so this is s minus a and this is s minus b. So in conclusion, if this is the point where the incircle it touches the side, and this is the point where the excircle touches the side, then this distance here would be s minus a, and it would equal this distance here, which is also s minus a. And similarly, this distance s minus b equals this distance s minus b. In other words, if we take this blue point to be the midpoint of this side of the triangle, then this point and this point would of course be symmetric with respect to this point. And this point would also be symmetric with respect to this point, because this distance equals this distance. And since this equals this, and this equals this, then these two little segments would also be equal. And they would be equal to, this is c divided by 2 minus semi-perimeter minus a. And now when we substitute s by a over 2 plus b over 2 plus c over 2, and we expand this expression, we're going to see it's equal to a minus b divided by 2. And so, this little segment between the midpoint and the tangent point of the incircle is a minus b divided by 2, and this little segment here is also a minus b divided by 2. And therefore, the distance between the tangent point of the incircle and the tangent point of the excircle with this side is a minus b. So to recap, if we have a triangle with side lengths a, b, and c, and if we draw the three excircles for this triangle, then this is semi-perimeter minus b, this is semi-perimeter minus a, this is s minus c, s minus b, s minus a, and s minus c. And then external to the sides, we have s minus c, s minus b, s minus a, s minus c, s minus b, and s minus a. This is how I remember which is which. For example, if I'm wondering what this is, then I'm moving it here, of course, because this equals this. And here I can see more clearly what's going on. And now I know that if I connect this vertex with this tangent point, this is going to be the semi-perimeter. And it doesn't matter from which vertex I'm looking. For example, if I'm looking from this vertex and I'm taking the distance to this point, we saw that this is the semiperimeter. In the same way, we can show that this here is the semiperimeter, and also this here is the semiperimeter. And so when I know that this here is the semiperimeter, I just subtract c, this side, and then I get s minus c, and then I move it back here. So I know this is s minus c. And for the incircle, if I'm wondering what this is, if this is s minus a, or s minus b, or s minus c, I just label the vertices a, b, and c, such that the vertex c is against side c, and vertex a is against side a, and so on. And then I just take my segment and see which vertex does it contain. If it contains c, then this is s minus c. If it contains a, then this is s minus a, and so on. Today we're going to have two optional problems again. Consider a triangle such that this side has length a, this side has length b, and this side has length c. We took a random point on this side and we connected it like this. And then these are the incircles of the two triangles, this triangle and this triangle. And then this is the line that is the common tangent line between this circle and this circle. The question is, if this tangent line intersects this line here, then what's the length of this blue segment? And here's the solution. So I've put some notations on the screen. First one is that the length that we're looking for is x. This little segment here is y. This segment here, between this tangent point and this tangent point, is z. This segment is d, and this segment is e. Now we notice that we have some equal segments. For example, this e can come here. Also, d can come here. Y equals this segment, and y plus z equals this segment here. We even have more equal segments. For example, this segment here, x plus y, is the tangent from this point to this circle, and so it equals this segment here. Similarly, x plus y plus z is the tangent segment from this point to this circle, and so it equals, on this side, x plus y plus z. And finally, we have one more. This segment between this tangent point and this tangent point equals this segment here, because we have the following situation. See here, we have a circle and another circle, and a tangent to both circles on this side and a tangent to both circles on that side, and they're intersecting here. And there is a symmetry with respect to this line connecting the two centers of the circles and this point. You see, with respect to this red dashed line, each of the circles is its own symmetric image, and this line is symmetric to this line, because we have an angle bisector here, of course. And so this segment here would be symmetric to this segment here. In other words, it doesn't matter if we put the tangent line on top or on the bottom, this length is going to always be equal to this length. And so here, one of the lengths is this and the other is this. And so this length is 2y plus z. Finally, let's calculate a plus b minus c, but using these red labeled segments. So we get a plus b minus c equals, now a is composed of e and x plus y, so they're here. B is composed by x plus y plus z and d, so here they are. And c is composed by d, 2y plus z, and e, so here they are. Now in the expression below, we see that the e here cancels out with the e here. The d cancels out with the d. The y's, the two y's, cancel out with these two y's, and then the z cancels out with the z. And what is left is one x here and another x here. And so when we divide both sides by 2, on this side we're going to just get x, and on the other side we're going to get a plus b plus minus c divided by 2. So this is the expression we got. And a plus b minus c divided by 2, this is exactly the semiperimeter minus c. And so we got that x, this x here, equals semiperimeter minus c, which means that if we draw the incircle of the triangle, then this here would also equal to x, and this here would also equal to x. This is the second optional problem. We have a triangle and two of the excircles here and here, and they touch the sides at this point and this point. So we take this segment and we construct their perpendicular bisectors. So the perpendicular bisector of this segment is this, and the perpendicular bisector of this segment is this. So these two red perpendicular bisectors intersect at this point. And we have to prove that this line here that connects this vertex with this intersection point is actually the angle bisector of this angle. And here's the solution. First of all, note that if this side is c, then this length is semiperimeter minus c, and this length here is also semiperimeter minus c. And so these two segments have equal length. Next thing to notice is that because this is a perpendicular bisector of this segment, then this green segment equals this green segment. And finally, because this is a perpendicular bisector of this segment, then this yellow segment must equal this yellow segment. Now see what we've got here. This triangle and this triangle have exactly the same side lengths, and therefore they are congruent. And in congruent triangles, all corresponding elements are equal, including altitudes. So take this triangle and drop an altitude from this point here. Then its length is going to be the same as the length of the altitude to this triangle dropped from this same point. So this length of the altitude equals this length of the altitude. And now we're in this situation where we have an angle and we have a point such that if we drop perpendiculars to the arms of the angle, the length of these perpendiculars is equal. And we're wondering if this is angle bisector of this angle. Oh yes, because this triangle is congruent to this triangle. After all, they have a common side here. This altitude equals this altitude, and then the triangles have a 90 degrees angle here and here. And because they have two common sides and an angle that points towards the larger of the two common sides, then they're congruent. And because they're congruent, this angle equals this angle, and so this is an angle bisector as desired.